Okay. Okay, I'm online. Thank you for the presentation. Thank you for attending this presentation. Okay, I will go through the agenda. I will present who we are as a company at a glance. Then I will tell you the key highlights for the analog coverage needings, why we do believe that it is a key point in the development of our devices. Then I will present you our practical use case, our test vehicle we choose for the trial, and then we will have the main course of the presentation, which will be the flow details we went through in the trials, and then we will try to have some conclusion on the trial. Okay, ST is one of the biggest or the largest semiconductors companies. We employ around 50,000 employees. Roughly 20% of them are potential user-to-user audience or presenter, because we are in the R&D. We spread all over the world with the sales and marketing. There are some figures in the financial, and we are engaged into Responsible Business Alliance and United Nations Global Compact. Digging into the company, I belong to the application-specific product division, whose portfolio is spread in these main areas from the automotive application-specific, industrial and power conversion, motion control and drivers, and the intelligent power switches. Those are the brand badges we use when publishing our devices. And especially for the intelligent power switches, the test vehicle has been chosen in this field. Okay, roughly, the analog coverage is important for the devices development because of the quality. That is our icon, meaning that quality is key. We know that analog coverage will help us to detect manufacturing defects such as shorts, opens, parametric variations, and so on. We then ensure the product reliability, allowing us not to have return from field once we delivered the samples to the customers. We can also guarantee the compliance with the industry standards. First of all, in the automotive industry now, we are digging into the ISO 26262. We also had with the Siemens team some relevant discussion on the field. We enhancing the testing, we can then enhance the yield in the manufacturing, and okay, we enhance the testability. They are both tied. We do reduce the warranty cost because we deliver less defective samples to our customers. And then, as a cherry on the cake, we will continue to improve our flow, the knowledge in the processes, and innovation in our design and development. Okay, this is the presentation of the test vehicle. It is an intelligent power switch. In this case, we have a pretty small device with 4 high-side switches controlled by some logic, and with a lot of analog parts for the sensing of the currents, for the thermal over temperature protection, for ground and DCC wire break protection. So you see that other than the logic, the logic core, which is in charge of controlling the device, there are a lot of analog parts that are in charge of sensing and telling what is happening in the application and in the device. Okay, this is the flow Defectsim allowed us to implement in this analysis. I used some color coding to help sort out what is from what is as an input from our side as designers, which is colored in yellow. So we have schematics, layout models, netlist, the test suite itself, and a good netlist. Then there are the blue the blue boxes where I intended to put the actions of the tool. So what the tool is doing is creating the defect universe, is selecting the targets devices where to inject the faults. It is injecting the faults, it is simulating the defective netlist, and then it is performing the analysis. And the pink boxes are the outcome of the output of the device, the outcome of the analysis. So this is quite straightforward, and once exercised, we can say that it is a step-by-step flow which is easy to implement and to follow. Okay, of course, the blue part is the logging of the tool. It is not intended to be read in the presentation time, but it is reported to allow you to understand that the tool is really helpful when giving some output, with giving the idea of what it is happening in the device. In this case, this is the create defect site list phase, where the tool, knowing the structure of the netlist, knowing the PDK of our own technology, is extracting all the devices instantiated inside the netlist with all the number of instances and the defect that can be injected. In this trial, we used the standard defect injection, but we were told that we can also model some defect on our own if we are needed, if we need to model some some specific defect on our side. So it's an open tool. Okay. Then the tool will create the defect to simulate. So before it has extracted the list of the device present on the netlist, then it will create the site. It will create the defect to simulate into the list. And in these log files, you can see all the details of each kind of defect that it is been forecasted by the tool for each kind of device inside the netlist, with relevant likelihood, which is meant to the tool to decide when it is time to decide how to cut down the number of defects to inject. It is not, of course, possible to inject an enormous number of defects, but the more relevant will be chosen by the tool. And each defect, which is named after D1, D2, and Dn, it will be then in a .alter command inside the netlist, changed with the non-defective device. More than the log file, which are available for a deep investigation, it is useful the AMS result browser, which will present graphically the situation of the flow exercised by the tool. In this case, we have the coverage, the activity coverage that our test bench reached exercising the netlist under test. Here you can have at a glance the activity of each single device. So you can see if your test bench is good enough to have an activation of the circuit, because of course you can spot a problem just if you exercise the device where the problem is injected. In this case, this is a very early picture. You see that a lot of devices are not yet exercised. This is of great help because you can, looking at this, you can then refine your test bench and enhance the simulation coverage. All these results are coming from a fault-free simulation. Then you enter the step where you simulate the defect. So you simulate all the netlist alteration I showed a few slides ago. And in the log files, you can start to see, together with the defect-free test results, you will see also the results of the defective simulation. In this case, we have 7 tests. It is just one of the test benches run on the device under test. Of these 7 tests run on this particular test bench, one of these for the defect 7021 is failing. So the tool indeed is reporting that something has gone wrong with this simulation. Collecting all the logs from all the defect simulations for all the injected defects, we have this a picture like this again in the AMS result browser, where the hierarchy of the netlist of the device under test is showed with the relevant likelihood of associated defects and the defect coverage. In this case, the overall netlist was well covered. We have more than 95% of defect coverage. If I'm not wrong, in this case, we were simulating 128 defects, which means that almost all of these defects were spotted by the tool, by the simulations. Of course, where there is a lack of coverage, this means that either the device was not activated, and you can see that in the slide, in the result for the activity coverage, or this kind of fault cannot be discovered by the test implemented, which means, I will show you later on, that you can enter a loop to optimize either the test or the circuit itself. Yet another representation of the defect simulation. Here we have all the defect simulated. You will have all the 128 defects simulated with the ID, with a classification whether they are spotted or not, and which is the test name which is spotting with all the test result. One of the first things to be noted is that when you come to the test name spotting the defect, you can notice that maybe, if you're lucky, there is one single or a very little number of tests that will cover the majority of defect. In this case, you are able to reduce the test number, to reduce the redundancy. So you optimize your test suite, you optimize your test time. And a kind of similar logging is on the other side. This is the list of the tests, and these are the defects that are being spotted by each test. So if you will see easily that if there is one single test spotting all the device, is the golden test to be run. Of course, there will be a combination of tests to cover all the defect universe. This is very useful. This is sortable. This kind of representation is sortable. In this case, it is sorted along this column. You see, this is the lowest value allowed in the margin set. This is the highest one. Everything up and everything down is failing and eventually is spotted. In this case, it is not spotted because it is inside the limit, and no test it is spotting these two defects. In case we are in the shape of optimizing the design, we can think to enhance to enter some test point to spot these two defects. This is the loop I was telling you when you can try to optimize your coverage. I'm sorry. Okay. Starting from the analog design, the goal for an example is to reach more than 90% analog coverage. You exercise the first time the tool, and you gain the logging from the tool. Then, if you succeeded, okay, yes, the goal is reached. Otherwise, you can analyze undetected defect to maybe add some test. The tool, indeed, in the logging is available to suggest some spots, some nice spots to be exercised. It will give some information in the distance in between the good simulation values and defective simulations. So if they are greater than a threshold, the tool can suggest to add a test for spotting that measure. We can also analyze our test suite for redundancy. As I said, more test is not more accuracy, is not more coverage by default, but just if these tests are not redundant each other. We remove also the dummy devices. We can remove the dummy devices from the netlist. We can tell the tool which are the dummy devices not to insert fault in these devices because they are not used, of course, in the netlist, just in case of fixes. And then we can work also with the tolerance of the test. We can slightly enlarge if we are in the shape, if the specifications allows us, and we can spot them. Otherwise, we can, if we are early enough in the flow, we can also add some test points to be spotted at ATE exercise, at the final test as at EWS, and we can take the advantage of having a bigger coverage looping this way. So again, this is a loop ideally to be closed once more than our target is reached. This is one example of this kind of optimization. In this case, this is the good result. We have a pin which is when left floating, which has to settle to a certain value. In this case, it is driven by the tester machine. So when the good simulation was run, this pin as designed has to settle at a certain value. In the case of the defect number 440, it is a short, I think. Of course, in the log it is well highlighted. You can see that this node, this is a primary output for the device because we were intended to spot the analog coverage when on the ATE. So in this case, the primary output is stuck to 0. This allowed us to implement a test. Maybe it was not the case, but maybe in the final test in the AWS, there is no any test looking at this point. So in this case, this kind of failure would have not been highlighted. The tool told us that this one was a nice spot, a nice test to be added. And we also have the metrics for this, the metric for this exercise. At the very first run of the tool, on top of the 128 defect asked to the tool to be injected, we just detected 24 of them reaching a low coverage, a low analog coverage in the range of 20%. Having a look, as I said, looping that way, we found that the adding a test specific for this kind of measure, we were able to add to spot 9 more defects, which means that we improved our analog coverage from 20 to 27%, just adding one simple test, which is run along with the ATE final test. These are the results from the log files. As a final result of our test, of our trial, we at the end reached more than 95. It is the slide I presented before. More than 95% analog coverage, which is impressive, starting from a single test with the 20% with a full suite test reaching not all the device under test, but close enough. The conclusion on our trial, which was performed last summer, autumn, in a few months, was that indeed we enhanced the coverage. We closed some coverage gaps in the device. Consider that our test vehicle was a already available device, so we could work just on what we had. We didn't exercise, we didn't add test point, we didn't modify test mode and so on. We just improved the test suite to be implemented either in the verification or in the testing characterization phase. We were allowed to remove, add and modify tests, so to optimize the coverage. Overall, the effort and runtime was quite good because the tool more or less worked out of the box. We had just to refine few little stuff on our PDK because PDKs are always tricky to be managed by EDA tools, but it was straightforward, at least because we have the power of Siemens team on our backs. Also running defect free and defect simulation was straightforward because almost the same exact environment we had in our verification environment was used by the tool almost as is. And then it comes that the learning curve was smooth. We were 4 or 5 of us and 3 colleagues of the Siemens team. So thank you for your attention. And thank you to the Siemens team, Nicola, Vladimir, Etienne, who helped us having these bright results.
Yeah. Fantastic. Are there questions from the audience or the presenter? Okay. If there is no question from the audience, I will have one. Let's say typically AMS simulation runtime is usually long, depending on the circuit that you have. How much could you cope with a runtime that was sustainable, knowing that you simulate many defects?
Of course, the more you shift on the left, the better it is. So as soon as you start with the very early design phase, maybe at IP level, at small subcircuit level, it will be easy. It will be faster for the single simulation. And then the tool has also the opportunity to combine the results of sub-circuits or sub-blocks. And then at the end, if you start early, if you start at sub-circuit level, you will gain the result from the sub-circuits, and then you can leverage them on the top level simulations. As well as modeling is another chance we have, because the more you model in the design, the more you can took off from the simulation to be combined at the end of the process. So if you shift left, if you partition, if you do smaller and easier simulations to be run, it will be faster, it will be easier, and then the combining process allowed by the tool at the end will give you exactly the same results as we had on these top level simulations.
Thank you, Phil, very much for your answer. Are there further questions? If this is not the case, then I thank you very much
Thank you. Thank you to you and the audience.
for your